don't know if that's what it.
All right, let's head into God's Word. 1 Peter 4, 8 and 9 says, above all, love each other deeply, because love covers over a multitude of sins. Offer hospitality to one another without grumbling. Do you see this as the case in your relationships? And it doesn't matter if you're thinking about friends, family, significant or insignificant in your mind. So for me, I like just stopping and just pondering, meditating deeply about phrases like, what does it really mean to love each other deeply? Or in my life or your life, like, what does it really mean to that by showing that love, it covers over a multitude of sins, at least earthly speaking, it feels that way. Or like, what concretely does it mean for me to offer hospitality in my day-to-day life? What opportunities do I have without grumbling? And I don't necessarily need any feedback with it, but I think there's three phrases there that every time I hear these two verses make me think, and make me think deeply about love and showing that towards other people. Let's roll into 6.2. Some of what's in there we didn't do. Some of you weren't here, and others of you are saying, I'm not really sure how to set up this, that, or the other, so let's take a peek. Be specific. So from 6.2, where should we start? Don't just go everything. Let's pick something. Carl.
Okay, in number 1.
Yeah, sure.
I got started just fine, but then I got stuck after I found the base thing.
Sure, so let's just start at the very beginning. So the question says, show that 91 is a pseudoprime base 3. So I would say if you don't know the core congruence without looking it up or seeing the answer, something like that, that's probably the first issue. So Carlo, I'm assuming you got the first thing. Basically, we need to do what?
3 to the 91st.
Okay. So the issues with this problem is 3 to the 91st is a huge number. To just review, pseudoprime is a number that acts like a prime when used with Fermat's little theorem. So in this case, 91 is what, 7 times 13. It is not a prime number, but we're proving that it acts as if I was doing this with 3 to the 5th or 3 to the 7th, a number that is actually verifiable as prime. Carl's real question, I think, is there an efficient way to do this that gets a number close to 91? And when I did this problem, I did not get there efficiently. So I have 1, 2, 3, 4, I think 5 steps to get there. Do you want me to show you my work, or do you want to follow yours? I don't really care. What would you like, Carl?
I just found that 3 to the 6.
What do you mean? Like 3 to the 6 is what?
7.9.
And you're saying 729 mod 91 is 0? 1. And you said you tried to use that. Okay, so let's just take what you have. So if you took 3 to the 6th, and I would guess there might be another route to get there. You could go something like this, like 3 to the 6th to the 15th. And say, okay, if 3 to the 6th is 1, I should be able to take this and say it's the same thing as 1 to the 15th, and 1 to the 15th is 1. Remembering that I still have a 3 to the 1st that's kind of tagging along the whole time because we're only covering 90 of the powers instead of 91. You could take this original problem and say the other proof of this would be if I just want to raise 3 to the 90th power, I need to get 1. If I'm raising 3 to the 91st, I should be able to get 3. Both of those are sufficient and equal proofs. So I'm not really sure what your question is, Carl. At this step?
Yeah, where do we go?
Okay, so at this step, if you know that 3 to the 6th is equivalent to 1, I would say what you're doing is a direct substitution and saying, instead of 3 to the 6th, call it 1. And now take 1 to the 15th, because this entire 729 is equivalent to 1. Remembering that that is only going to take care of 90, because 6 times 15 power rule, with 3 that are left over. Now, I'll be honest, when I did it, I didn't find that because I stopped at 3 to the 5th, didn't find it, got frustrated, and just said, all right, 3 to the 5th is something, raised it to the 18th power, and just plowed through and did not get there efficiently. This is probably the textbook. Like, is this the way that you have in a PDF? Like, did it show you this? I don't know. Okay. The answer is just that you prove that at the very end you got 3 mod 91. Because 3 mod 91 is a proof in Fermat's little theorem, if you're raising it to 91st power, that it acts like a prime even though it's not a prime. So it's one of those kinds of problems that reminds me of the first time we saw something like this in pre-calc. Like, the problem is actually the work to get there, because you know, or hypothetically know how to set it up, and you know what you should end up with at the very end. Like, this is the beginning and this is the end, and you have to show to get there. Go ahead, Lizzie.
When do you use that thing when you subtract 1 and then put around there? Like, we have like 3 to 90.
So it's the same thing. So if you're trying to prove that something is a prime or a pseudoprime, the vessel to do it is either take the prime, pseudoprime number, power, and mod, or 1 less, keep the mod the same. Keep going there.
If you multiply 3 to the 90th is congruent to 1 mod 91 by 3, you get 3 to the 91st is congruent to 3 mod.
Like, it should make sense that multiply this side by a 3, you get this. Multiply this side by a 3, you get that. Either one. It doesn't matter. It's the same thing. So I would say there's 2 parts that this is good review, and just going through some pieces. I would say the first part of it is knowing how to set it up, like what the world's going on. And then the second part is how do you efficiently get to where you need to go. Okay? For your test to come, my plan would be something at this kind of level, like prove something is a pseudoprime. I'll give you something like this. I may or may not say use this base or whatever it might be, but even though we are going to do some things with strong pseudoprimes or absolute or Carmichael numbers and stuff like that, this is the core idea I want you to be able to do. Go ahead.
That is not how to do the book.
This is not the method. Okay. Is it worrisome? Okay. I do too. Do they take 3 to a certain power?
3 to the 4th times 22, or 3 to the 4th to the 22nd times 3 squared.
Sure. And 3 to the 4th gets you nowhere, right? Yeah. Okay.
Well, 3 to the 4th is negative 10.
Sure. Which I guess is better than 729, or yeah. Okay, let's move somewhere else. Not the first problem or 2, somewhere else that you want to see something. What?
I said there's only 4 problems, right? Number
5, right?
12.
Wasn't it 1, 3, 7, 12, 16b?
1, 9, 12, 16.
Oh,
Look at 12. Yeah, look at 12.
Sure. So number 12 says, show that 25 has a strong pseudoprime to base 7. So let's just start off with the part that you should know how to do something with. So anytime you see this word pseudoprime, there's got to be something that rings a bell, like fundamentally I need to still set up a certain kind of congruence. So let's roll. So for number 12, the beginning of the problem is probably saying what to the what is congruent to what. This kind of goes back to Lizzie's question. Don't worry about strong. Like if I just want to prove it's a pseudoprime, 25 is the composite number that's going to act like prime in base 7. Nick, what's my congruence? .25 is a pseudoprime in base 7. How do I set it up? Okay. So first part of the problem is, does this work? Because it's not a strong pseudoprime if it's not proven as a pseudoprime at the very beginning. Okay. Let's just go 15 seconds. Turn and talk. What's your plan? Like, how do you get there efficiently enough? Okay, so let's hear a couple routes, and then I like my route in this case. I'm guessing it, once again, is not what's in the back of a book or on a PDF or whatever it might be. So give me a path to break down 7 to the 25th without just saying a big calculator or a big computer can just do it. Go ahead.
7 squared is -1, so 7 squared is 12.
Okay. So I like the way that he went at it. You don't necessarily have to look for 1. -1 is probably just as valuable. So 7 squared is 49, and 49 is 1 less than 50. And you have your answer. I mean, like, the first part of the problem is done because negative number raised to a positive power, you get, or an even power, you get the idea. Okay. The second part of the problem we have not talked enough about. So to prove that it's a strong pseudoprime, you have to be able to break down 1 less in a certain way. So I'll do some bad pedagogy first. Say, because 24 can be broken down into a power of 2 and something that's left over, I can use this piece to do something else in the future that I'll explain. Correct. So you want to go further? Okay. So it's kind of like, okay, it passed the first test. That's all we really did at class on Wednesday. Let's move forward a little bit. So I'll go back. This is the key idea that I want you to be able to use, like to know that when you see pseudoprime, this is the test. It's built into Fermat's little theorem, and there's many paths to the answer, some more efficient than others. So just so that you've kind of practiced or seen a variety of different things. Here's where I want to go first. We'll wrap up 6.2 extension stuff and then show you the phi function for today. Here's where I want you to go. So what's Fermat's little theorem? What's it show? If you want to go a little bit farther, and that's it seems like I'm belittling your intelligence, what's that video? Like, what's the visual representation? What's that show? But I want you to talk this way first. And then I'll bring you back together. Sure.
I don't remember that.
Steve. Sure.
And that's actually what was screwing me up.
Sure.
So I was thinking, but now I get it.
I'm okay with that.
All right, Dylan, start us off.
Well, I guess from what Aaron said, it says that it isn't prime.
So it is debate about, like, does it show whether a number is prime or does it show that a number is composite? Let's keep going, Aaron.
Well, I believed it until we heard about pseudoprimes.
Okay, keep going.
You can, with Fermat's-Little theorem, you can prove that a number is composite if it doesn't fit the formula, the pattern.
So you have an infinite number of composite numbers that will not fit into Fermat's-Little theorem. So at the superficial level, like, you can throw out a lot of numbers that you know are not prime.
Because it's true, if the number is prime, it's always true. But sometimes composites, it's also true for. So if it's false, then you know a number is composite.
Okay, I want somebody to tackle the second question, like the purpose of the beads thing in that video. Was the video Wednesday or Monday? Friday? Kira, were you here when we watched the video? Hey, mentally unsure. No.
No, I remember what I had. I was doing taking
Okay, so it had to do with the idea like a prime number can't be easily broken into different kind of strands that aren't prime. And through the rotations and unique representations of what you can create, there's a lot of ties into what's behind this theorem. Like, you can only create this many variations of the necklace. I'm going to go back to, like, maybe that visual representation doesn't connect with you in any way because you don't really care about beads and necklaces. But the reason I like the video is because I do think that you can take this theorem on superficial level and crank out an A. And for some of you, that's your goal. Like, I think you can crank out an A. Or a high B+, hypothetically. But I want you to be able to see it in another way than just, okay, so this proves this, which proves this, which proves this. There's two things that are built into it. I'm actually going to skip this and move into something else. Let's go here first. I changed my mind. In order to absolutely prove something, and absolute probably should even have quotes on it, there's something that's called a Carmichael number. Actually, what I want you to do are, let's just make a number that would just kind of satisfy what's going on here. So you have to have at least or more than two terms. These numbers have to be distinctly prime, and this kind of a relationship is going to have to hold true. So, for example, if I picked a number like 30. Give me the prime factorization, like what times what times what. Okay. If I take 30, which is my n, and these numbers, which are my q's, 1, 2, and 3, I should be able to take it so that any of those q's subtracted by 1 should go into the number 1 less. So I'm going a direction with, go ahead, Aaron.
Can I back up and ask a vocabulary question?
Sure.
Carmichael number is also what they would call an absolute prime.
It is the same thing.
Absolute pseudoprime?
It's one and the same. Yes. Okay, so let's see what issues we have. If I take and pick one of these factors, let's just take the 5. I subtract 1 from it. I have 4. If I take the number, subtract 1 from it, I get 29. What did I just show or not show? Go ahead. Okay. So I probably could have backtracked and said it shouldn't even pass the Fermat's-Little theorem. Like if I take 2 to the 30th, I'm not going to get to 2. Okay. So now let's pick a number that I know is going to work. I think we did this one in class 561, maybe on Wednesday. Give me some prime factorization of this. What times what equals 561? Okay. So now run it through the algorithm. So I could take any of those factors and see that they divide into what? Emily? So for example, I could take, go ahead. Or say, okay, so let's answer the tough question. That's, what did that prove? And if you want to go more negative, like, who cares? I don't really care which way you want to go with it. Discuss. I'm just hypothetically looking at you, Lizzie. It's fine. I'll make a little bit of sense out of what you just said from this, because I think these two ideas go together really well. Right. Okay, so to me, I have this like, what comes first, the chicken or the egg idea that's going through my head. But anyways, it's a strong pseudoprime. Like, it is a pseudoprime. It passed another test, and if you're going with like, why does it matter? It's going to be able to work for more bases than just like, it's a strong pseudoprime in base 2, or it only works in base 3, because if it fits, like, it showed as a prime even though it's a composite, and I can build the factors and all the factors work in something like this. It helps me figure out what the next pseudoprime is, and I can pick numbers, and this is where I threw a slide up last time. It made absolutely no sense. Or I could take the original number and whatever base I want, so anything that's relatively prime to 561, and it's going to fit within Fermat's little theorem. So in other words, this is a strong enough composite number that acts like prime, which is a pseudoprime, that I can do almost every base and have it work. Go ahead.
I'm wondering, what are the bases that won't work? They're bases that are multiples of the, in this case, the 3 primes.
I would say the divisors of it.
3, 6, 9.
Right. So if you go back into like, this is built off of 3, 11, and 17.
So 3, 6, 9.
Right. 11, 22.
33,
right.
17, whatever.
And all the combinations of thereof.
Sure.
So I can take 2 to the 561 and get to 2. I know it'll work.
So
I can take 4 to the 561 and get 4. It's going to work. I can't take something like 33 and expect it's going to always work. But it's a stronger pseudoprime because, or an absolute pseudoprime, because there's more than just one loophole to prove that it's composite or prime, depending on your perspective. Go ahead, Aaron. I don't want to go too much further with it.
is it the linear combinations of 3, 11, 17?
Yes. Yes. Okay. So I'm going to go back to, at this point, it's not my intention that you have to go this far with a proof on a test or something like that. But I want, like, for me, I like this, even though it may be something that confused you in your assignment, that just saying, like, I can take a base and raise it to a power and it's just going to magically work sometime and not work sometimes is very vague. And this somewhat hones down to, like, in some cases, I can play with a number and know that more than one case is going to work. Now, I'm not going to redo what we've already just talked about, but I just want to show you a different example and I actually want you to kind of take the ownership of it. So 2821 is another Carmichael number. Look at the three things that I have there, have a quick discussion, and, okay, makes sense, makes sense, makes sense. Have a talk. Go. I don't want to do more. I really want to do fees because they're fun.
Okay, we can do that.
No, we won't. Go.
With the Carmichael numbers, there's the bit about for the base 2 to the n minus 1 is the next Carmichael.
Yes, we're getting there.
Is that true for any other base? Or is there something like that?
I don't think it's true for any other base. I think it has to do with the fact that for Carmichael numbers, the one less has that like 2 to the power divisibility.
Sure.
I don't know if that's the right word.
And then back at number 12. We got that far, where we set up.
Oh, sure.
The other illustrative things like the test, that's one of this.
We're getting there.
Yeah,
Yeah, I'll do one more thing, and then I think it'll at least make somewhat sense. All right, here's my question to you. What's B? So I think most of you are like, oh, cool, this works. Man, you just kind of, at least for me, like glazed over, like, B is, go ahead. So anything that's relatively prime will work. It isn't necessarily everything that will work, but once again, relatively prime to this, this, or that. Okay? Which leads to the final piece. So a strong pseudoprime is a pseudoprime to base P that also passes Miller's test. So if you really attempted to try to get all the way to the finish line of number 12, there was this idea built into it. If I take the n and subtract it by 1, so I'm just going to throw a couple things up there, like 560 was one of those numbers, like 1 less than the number that's there. I have to be able to break down 2 to a power and something that's left, where the something that's left, I'll just go this way, is odd. I don't know how to make this so it doesn't feel very, very abstract. I guess by the time you leave, I think it'll just be somewhat abstract. And the base that's relatively prime raised to that what's left that's odd is equal to 1, or the base raised to the other portion is equal to 1 or negative 1 in that same mod. Now I'm going to go back and say you're taking a number and it's just another way to show what's going on within that number, and it's used by mathematicians to find, and maybe you heard Aaron talking about this, the next number after 561 that's a pseudoprime. So I'll go like 5 steps back and say, what I want you to know is there's this test that shows whether or not something's a composite. You can go a little bit deeper with various things with it. Miller's test is really another way to show whatever it is that you're looking for. So, for example, I'm going to take 45. And the question is 45 a pseudoprime to base 17? Okay. If I broke down 45, I get 2, or 44, I get 2 to the second times 11. So far, so good. Like an odd number and 2 raised to a power. Okay, we'll get to do something with it in just a second. What I also would need to prove before I even go anywhere with it is if I take 17 and raise it to the 44th, or take 17 and raise it to the 45th, it still has to pass that Fermat's little theorem idea. So I actually want you to just test one thing for me. Use your calculators, test my math. 17 to the 4th, I'm saying is 1 in mod 45.
Yes.
What? Then we'd have no, we wouldn't. The idea of Miller's test then is I can take one of those bases. In this case, it happens to be 17, and I can raise it to either the 2 to the second power, which happens to be 4. Like, I kind of threw it at you like, hey, just pick this and test it. But the reason I picked 4 is because Miller's test says if it is, I should be able to take the 4th power, like this 2 to the j, like I should be able to take this and get a 1 from that piece that's there. Now I'm going to kind of just stop and say, I'm okay if you're at, I kind of get it enough to nod my head. I'm not sure if I want to set up and do 13 of these myself. Aaron.
And j has, 2 to the j isn't necessarily 4, is it?
No.
J can be...
J or S are kind of interchangeable in different contexts that I've seen.
From my reading, you have a 2, any integer from 0 to s, or 0 to something, 0 to 0 to t.
But I would still go with what I've seen or researched with most of it is like usually you're going to take that full amount and test it. I guess I'm just going to kind of leave it there. I have a few slides in here that are the excerpts from your textbook. I'm not going to take time to go through each of these, but these 2 or 3 slides are the exact same thing about like what base are you going to pick, why would you pick something that's divisible or not, just kind of taking the pieces out, because I want to go back to like, okay, so here's a review. Pseudoprime means this, Carmichael kind of means this, Miller test means this. I think this is a good place for either making your notes look decent or putting some connections together. So here's the full picture in one slide. I do want you to talk again. As far as you understand it, this means what? Here's a test that shows what, and then you think that this kind of means what? Go ahead, put some pieces together as best you can. I can help you too, or answer your question. Go ahead.
I think I understand the pseudoprime idea, and I think I understand the Carmichael number, but the strong pseudoprime, I think, fits somewhere in between those two, and I don't understand who's the pseudoprime. I would suggest it's fine if it's not.
I would say the way that my mind puts it together is more along the lines of, okay, 1 level, 2 level, and I see this as, like, in my mind, I see it as I can stop at this point and understand what a strong pseudoprime is. Because it's this, it will also pass that.
Are there strong pseudoprimes that are not Carmichael numbers? Like, if there was a Venn diagram of Carmichael numbers and strong pseudoprimes.
I think the answer is no.
So, strong pseudoprimes is more restrictive than absolute prime?
Absolute pseudoprime?
Yeah.
I don't know.
And a lot of times, like, when I see something and I'm like, is there any practical use for this? This is so stupid. And then, like, 3 lessons later, you start using it for something else. Is that one of these things?
Probably not. I don't have the magical connection. Here's a big concept that the new thing that I would like you to be able to use moving forward. The only new concept that we're going to talk about is the phi function. The reason it's called phi is because of the Greek alphabet. It is that 0 with a line through it. I've seen it with vertical or a little bit to the side. If you're a Greek person, I don't know, should it be one way or the other? Okay. The word that got cut off is and that, but I'd like you to make some sense out of it. So what does this mean? Like, for example, if I wanted to find the phi of 10, What does that mean? And there is a chart somewhere in the back that has all of the phi numbers. I have page 609, 610. If you want to see if you're right. Okay, so the answer is 4. So let's kind of talk our way through it. So it's what are the numbers that are relatively prime to 10 in this case? If I'm just making a quick list of the 4 numbers, it will definitely not be any of the even numbers. So if I look at the odds 1, 3, 5, 7, 9, the only one I throw out is what, 5? So because of 1, 3, 7, and 9, all of those numbers do not divide into 10, so number of relatively prime numbers. This is definitely one of those things that, okay, so I can just plow through answers like the phi of this is this, and the phi of this is this, and the phi of this is this. That does have applications for an efficient way to solve a congruence. Because 9 doesn't divide into 10. They're relatively prime, like. Right. So how many numbers up to 10? I mean, like, you can count 10. It doesn't really matter because 10 will never... 10 goes into 10. Right. So let's make some sense. I actually want to kind of divide stuff up here. You have the same thing in your chart where basically you're just looking for how many numbers are relatively prime or whatever it might be. I have all of the answers up through 12 done because I didn't think it was worth a ton of time with it. I'd like you to just pick a couple of them. So for example, let's take 12, 7, and 10. And I'd like you to not only like figure out answers, but I'd also like you to figure out like some method to the madness. Like, oh yeah, 7 makes sense. I get it. Oh yeah, I get it. 12 should be this because of that. So not only what are the numbers, but can you start drawing some conclusions, creating some theorems or some conjectures? The reason I have all 12 up there is because you can probably verify something with a different answer. Okay, so now let's put some things together. Let's start with the easiest one. That I think it's 7. Give me, like, this makes sense that... Go ahead, Kira. Because every number should not be able to go into it. So if that's the case, I should be also able to look at a number like 5, and I'm still got what she said, or 3, and I still see what she says. Okay? 12 and 10. Give me something you figured out. I'll give you a different hint with it. I'd like you to start with 10 and use other numbers on this chart and make a conjecture that probably is going to be true. Like, okay, you can write the numbers out we already did, like 1, 3, 7, 9. It's 4, but if I have all the numbers up to that, there's a couple numbers in here that I could use in order to get what I'm looking for. Kira, you had an idea, and then you put your hand down. Go ahead. You're on the right track. It is not addition. Go ahead. Sorry. So whether she knew she was right or not, Euler functions are multiplicative. So the difference between 5 and 10 is going to be nothing that's larger. So like there's something behind, okay, 2 is this and 5 is this, so 10 is this. Okay, but if that's the case, I should be able to do something to get 12. I don't disagree with what she said, but don't write down like, because this is 1 and this is this, that this times this always equals this, because you look at it and you're like, well, I don't get 2 times 6 gives me 12. However, 3 times 4 does. So, conjecture. It is multiplicative, but you have to pick the right numbers to make it work. So, why would you do 3 times 4 and not 2 times 6? Like, draw some conclusions. Take a guess. Like, indirectly, you're doing inquiry math because you don't know what's going on. But in the end, you're going to have these theorems at the bottom of the slide that, oh yeah, I knew that. Good. Kira. So are 3 and 2. Go ahead. I'm just playing devil's advocate. Like, you're on the right track. Keep going, Dylan. Say that again?
3, 2, and 10.
Okay. I think that's incorrect, but we'll keep going.
They don't. Well, they are, but I meant like they don't multiply to 12. I know.
Okay. So I'm just going to go with think prime factorization or factors in general, and 2 isn't going to get all the numbers that 4 is going to get. So 2 times 6 isn't as efficient in this method as 3 times 4 because, go ahead, I need the prime factorization in the largest variety as I can. So I need 4 times 3. I don't need 2 times flip the other way 6. Now I'll put a couple more, like this works and this works. Here's a statement that's already on the screen. The maximum value of phi, if the n you're checking is even, it can't be any bigger than half of that n. Make some sense out of it. Why is it? It can't, if I'm checking 6, it can't be bigger than 3. If I'm checking 100, it can't be bigger than 50 or whatever it might be. Gabe? So every even number is relatively imprime, relatively composite to it to make up a term. Okay. Let's go a little bit further with it. If I wanted to make a reduced residue system of a bunch of phi integers such that every element is relatively prime and no 2 elements or whatever. 1, 2, 4, 5, 7, 8 is a reduced residue system of mod 9. To make sense out of it, it's just basically saying, okay, all of these numbers are relatively prime. If I'm in mod 9, numbers like 10 act like 1. So here are the least residues. There's other options that will also be the case. If I have a reduced residue system in mod, whatever it might be, where each of those numbers are relatively prime, then multiplying it by some number is also a reduced residue system. So I actually want you to take and make some sense out of this. So for example, I think you're good enough, like, okay, 1, 2, 4, 5, those numbers don't go in it. What this is saying is 2, 4, whatever, also are going to act the same. I want you to play the game of, why does this work? And why does it make sense? So in other words, the phi of 9 is 6. If I multiply it by 2, I get 6 numbers, and that's still a least residue system because it's the same 6 numbers. Go through it, Emily. So now make another leap because you already knew that was the case because you've done a bunch of problems where if x is congruent to 3 mod, I actually don't want to go too far with this. The idea that I can multiply something and still have the same value is already ingrained into what you've already known. 2 minutes. One more thing. Let's go here. I'd like you to take a peek in your book, Theorem 7.3 and 7.4. If somebody has a page number, let me know. Because to take what you have and be efficient with it, knowing where this is going in the future is going to help you with what you have to do in the past. Okay, so I'll say it a different way. There are definitely more shortcuts that we haven't even touched on yet. Now, what I'm basically saying from you is I'm not going to give you all the keys to the castle. There are efficient or inefficient ways to go at it. Even though this is in the next chapter, it's kind of like you're expected to do things very, very inefficiently in this section. But there's much more that's still to come. My plan for the future with dates is this. We're only going to do section 7.1 as the combined chapter 6 and 7 test. We need 2 days to make sure that our heads are on straight, that we know what's going on with it. That probably means that you're close to finishing 6.3 for Monday. And then that Monday and the following Monday will be 7.1. And then you can kind of decide whether the next test is going to be the Wednesday or Friday of that week after Thanksgiving. So it won't be the first day back from Thanksgiving, but most likely the Wednesday after Thanksgiving, where will make sense through using the phi function. Kind of like with 6.2, I'm fully expecting that you say, like, okay, I was okay with this and finding least residue, but I had issues because I don't quite understand that. And I'm okay with that because even though you're not quite done with it, I still think you can do some problems with it and have some moderate success. Enjoy your weekend. We'll see you on Monday.